you might have noticed that some types of electric trains make pretty interesting noises as they accelerate. Noises that sound kind of like this. Now, the exact sound depends on the type of train, but what they all seem to have in common is that it's got these rising pitch tones, and then there is these sudden changes in pitch in between that kind of sound as if the train is shifting gears or something, which of course is not the case. Like, if you've been on one of these trains, you'll know that it's not actually shifting gears because you don't feel a change in acceleration as it makes these shifting noises. It's purely the sound. The acceleration of the thing is smooth and continuous. It's just the sound that it makes that has these random shifts in pitch. So I thought it'd be interesting to take a look at not only why these trains are making sound, but specifically why they're making this type of sound. And that's also going to involve seeing if we can make this type of sound ourselves. So I think the first thing we need to ask ourselves is, where does the noise actually come from? Like, what's actually making this noise from the train? Well, it's the electric motors. So if you have an electric train, you can have electric motors that are attached to the wheels and they drive the thing, right? And you're going to need to power those motors. Now, what you don't want to do is hook up the motors directly to some kind of a power source, like an overhead wire or a battery, or in some cases a diesel generator. You don't want to do that because you want to be able to control these motors, right? You want to be able to control the power output of these things because you want to control the speed and the acceleration of the train. You don't just want to hook them up directly to a power source and run them at full power all the time. So you're going to use motor drives, devices that are specifically designed to control the power output of electric motors. And the way that these motor drives do this, the way that they control the power output of a motor, is by very rapidly switching that motor on and off, which is obviously called pulse width modulation, as I'm sure a lot of you watching this channel will know what that is. It basically means you take something that you want to power and you turn it on and off very rapidly. And by varying the duty cycle, which is the ratio between how much of the time the thing is on versus how much of the time the thing is off, you can control how much power it receives. And this switching is done typically in the thousands of times per second, depending on the application, right? It could be hundreds of times a second, or it could be tens of thousands of times a second. In a train, it's usually going to be in the hundreds or in the thousands of times a second. And so what happens is, each time the motor gets switched on, the electric current through the windings will rise up. And each time the motor gets switched off, the electric current through the windings will decay back down. And so the electric current in that motor is constantly going up and down like this. But of course, electric current through a motor winding generates a magnetic field and generates all kinds of magnetic forces inside of that motor. So if the electric current is going up and down like this, then all of those magnetic forces are also going up and down. They're also changing at the same rate. And that means that the windings in that motor will vibrate at that same frequency. And that vibration produces an audible sound, right? And that's the sound you actually hear. That's why the motor will produce sound. It's because the current in the windings is going up and down, so the windings vibrate a bit, and that vibration is actually what you hear. And so the tone, the pitch that you hear, is the frequency at which the switching is being done, right? So if the switching is done at 1000 Hertz or 1 kilohertz, that means you're going to hear a 1000 Hertz tone from that motor. Now this phenomenon doesn't just exist in motors, it also exists in all kinds of other things, like power supplies, for example. They have coils inside them too, and those coils can make noises like this as well, which is why you sometimes hear a whine or a buzzing noise coming from a power supply. It's just because there's some coils in there that are vibrating. Now, I've seen people explain that the noise of the train comes from the switching electronics, which is, it's not entirely correct, because yes, the electronics are responsible for the sound being produced because the electronics are doing the switching, the motor drive, right? But the sound itself originates from the windings inside the electric motor because they are actually physically vibrating. So the sound comes from the electric motor. The reason the electric motor makes the sound, that's the electronics. Okay, so we now know why the train makes noise, which is good, but we don't know why it makes that particular kind of noise. To understand this, we have to dig a little bit deeper into how these motors and drives actually work. So, the trains that make this type of noise use AC electric motors. So these motors need to be powered with AC power, actually three-phase AC power, but let's just not worry about that for today's video and pretend that they're just single-phase machines. It'll make things a bit simpler, and the fact that they're three-phase is not really important for what we're talking about here. So your drive, your motor drive, will take some DC source as an input. That's usually the overhead wire, but it might be rectified into DC first if the overhead wire is AC, doesn't really matter, and then it converts that into AC that powers the motor. Now the AC that powers the motor needs to have a variable frequency and a variable voltage depending on the speed of the motor. So, let's say the train is in the station, the motor is off, and we want to start accelerating. What will happen is the drive will first apply a relatively low voltage to the motor at a low frequency. And then as the train, and therefore the motor, speeds up, the frequency and the voltage will ramp up. So the drive will apply a higher and higher voltage to the motor, and it will also increase the frequency. And that's how, essentially, you drive an AC motor. The question then is, how do we make that variable frequency, variable voltage AC? Well, that could be done using a circuit like this. And we've seen the circuit before on this channel. It's called an H-bridge. In this case, because again we're talking about a single-phase scenario, it consists of 4 switching devices. Now these switching devices are going to be some kind of transistor, some kind of thing that can switch many times in 1 second. And essentially what you do is you connect your load, in this case that would be the motor of your train, you connect that in the center. And so if you put the switches like this, then the current flows through the load this way, and if you put the switches like this, then the current flows through the load the other way. And so by alternating between those two states, you make AC power and you are powering your AC motor. The problem though is that the AC power from this H-bridge is not going to look like this, it's going to look like this, right? It's going to be a square wave because these switching devices can only be on or off. They can't be anything in between, or at least they're really not supposed to in an application like this. But that gives us a problem, right? Which is, how do we make a smooth sine wave to drive our motor using switches that can only be completely on or completely off? Well, I'm sure a lot of you watching this channel will know of a technique called SPWM, or sine wave PWM. And it's a method that you can use to create a sine wave using pulse width modulation. So remember that way back at the beginning of this video I mentioned that if you switch the power on, the electric current through the motor winding rises, and it doesn't rise instantly, it takes time to ramp up because of the inductance of the winding, and when you switch the power off again, the electric current will fall back down. So what you can do is, by carefully crafting a sequence of short pulses with varying lengths, you can shape the current into a sine wave. And of course, the shorter you make these pulses, the higher the frequency of your pulse width modulation, the cleaner the quality of that sine wave becomes. So with this technique, we can make a pretty nice sine wave, and we can also do it at pretty much any frequency we want. So let's try this out for ourselves on my homemade inverter that I built a couple of years ago for the grid-tied inverter project. I've programmed it to do this sine wave PWM technique, and I've attached it to an old table fan, which is going to be used as the motor that we're going to power. Now, I've mapped this potentiometer to control the speed of the motor. So when I turn that potentiometer up, the inverter is going to increase its output frequency and at the same time increase its output voltage. So as you can see, it works quite well, and it produces a noise, right? The motor produces a 1000 Hertz tone as it runs. And the reason for this is because I chose 1000 Hertz for my PWM frequency. If I make the PWM frequency 2000 Hertz, it sounds like this. Now 1000 or 2000 Hertz is a pretty low frequency to be switching at. Much more typical for these medium power applications. When I say medium power applications, you have to think about things like electric bicycles, electric cars, industrial motors, or like smaller industrial motors, kind of stuff like that. It tends to have a PWM frequency of around 10 kilohertz, 10,000 Hertz, which sounds about like this. It's much more quiet than switching at 1000 or 2000, and that's because of two reasons. First of all, the faster you switch, the smaller the changes in motor current will be, the smoother your sine wave will be, so the less vibrations there will be in the motor winding, so it actually just makes less sound when you switch faster. But on top of this, human ears are worse at hearing higher frequencies. Most humans can only hear up to about 15 to 20 kilohertz depending on your age. So if you have a motor drive that's switching at 15 or 20 kilohertz or even 25 kilohertz, it doesn't even matter that much how loud the noise might be, because it's just outside of your hearing range, and so you won't notice it anyway. So faster switching for those two reasons will lead to way less sound being produced. But nothing that we just heard sounds quite like one of those trains pulling out of a station, so clearly they're doing something else. And that has to do with their switching frequency. So the problem with an electric train is that a train is a pretty high power application, so these kinds of drives need to operate in the thousands of volt range. They also need to operate at thousands of amps of continuous current. So very high voltages, well, it's always a relative thing, right? Compared to a transmission line, it's still nothing, but you get the idea. Relatively high voltages, high power, and generally speaking, as a rule of thumb, the higher the voltage gets, the more difficult it becomes to make very fast switching electronics. So a lot of trains, as their switching devices, are using IGBTs, and IGBTs are not great at switching very fast, and when you're using an IGBT, again, the higher the voltage, the worse it gets at switching fast. Now, this is changing a bit now because more and more trains start to use silicon carbide MOSFETs, which are much better at switching fast, but most of them in use now are still using IGBTs, and they're just not good at switching that fast. So the switching frequencies that you see in a traction drive for an electric train motor is typically not 10 kilohertz or 15 kilohertz. It's going to be more like somewhere between 500 and a couple thousand hertz, so much lower switching rates. The problem with that is, let's say we have a sine wave, and we make it using a relatively low frequency PWM carrier, kind of like this. Now, in this particular case, the PWM pulses kind of happen to match up nicely with the period time of our sine wave. But now what if the train speeds up and the sine wave's frequency becomes bigger, so the period time gets shorter, but the PWM frequency remains the same, so our PWM pulses are no longer matching up that well with our sine wave output, and the whole thing just becomes kind of a mess. And this will introduce additional distortion, additional noise, and it's just not very good. Now, this is no problem if the PWM frequency is very high. Right? If the PWM frequency is much higher than the frequency at which the motor is running, then who cares that the pulses don't quite match up with the sine wave? It's not that big of a deal. But when you have a very low switching frequency to work with, and the pulses last quite long, it just becomes a great big mess. So what if we used a different approach? What if we didn't use a fixed PWM frequency that always stays the same, but instead we just use a fixed number of pulses for one period of our output signal. And so as our output signal goes up in frequency, the pulses get shorter along with it, and the whole thing just scales like this. That way, the PWM signal is always matched up perfectly, is synchronized to the output signal. And this is called synchronized PWM. If I implement this on my own inverter, speeding up the motor will sound like this. So this sounds a lot more like one of those trains accelerating, but it still misses that key ingredient. It misses those sudden drops in pitch, right? Those sudden gear shifting sounds. Well, that's because on my inverter, the switching frequency is pretty much unlimited. Well, it's not really unlimited, but it can go up to around 25 kilohertz, which is pretty high. And so I can just keep ramping up the speed of this motor, and the PWM frequency happily goes along with it, and we don't really run into the limit of this thing. But of course, we don't have that luxury on the train's traction inverter, which is severely limited in switching frequency. And so as the motor speeds up, the pulses get narrower and narrower, and at some point we start running into the zone where the switching becomes uncomfortably fast. And so what are we going to do at this point? Well, the solution is kind of obvious. We just drop a few pulses. Who cares, right? So if we were doing, let's say, 10 pulses per period, we just drop a few of them and we move on to 6 pulses per period. And now we have some headroom again, and we can continue to ramp up the frequency. And so when you drop a few pulses, obviously your PWM frequency suddenly drops way down. Drops down a few octaves actually, and that's why you hear that sudden drop in pitch or that gear shifting noise. Now, of course, it depends on the manufacturer how many times they want to do this. So if you're comfortable with having a pretty wide range of PWM frequencies, you might only have a few of these jumps through the entire course of accelerating from 0 to full speed. But if you want to keep the PWM frequency within a much smaller range, well then you might have to drop pulses very often, so you get lots of steps. Also, you can decide at different moments when you're going to do it. When are you going to move on to the next stage, the next number of pulses? And it's things like that that give the different trains a unique sound. Speaking of which, there's actually, I found out there is a genre of YouTube channels that are dedicated to like building inverters and driving motors to accurately reproduce the sound of specific trains, which is kind of fascinating. A lot of these seem to be Japanese, by the way. I'm not sure why that is. I think a lot of these high power train inverters are actually Japanese products, so that might have something to do with it. But anyway, check out these channels if you want to see more stuff like this. So this is why a lot of these trains make these interesting noises as they accelerate. And I have to say, I'm a fan of these noises. I like the way they sound. In the future, we'll probably get less of this because the electronics will get better at switching fast, like I said, with the silicon carbide devices. I imagine someone watching this video 80 years into the future being like, what is he talking about? Noise from a train? Trains don't make any noise. Anyway, I hope you've enjoyed this video. If you did, maybe consider clicking the like button or perhaps subscribing to this channel even. And of course, thank you very much for watching.